Hey guys, this is Mr. Markarian, and I just wanted to let you know that I understand if you're struggling with equilibrium calculations. I thought to maybe alleviate some of the fear and anxiety of working one of those problems, I would present this video dressed as a fond memory of a childhood character, from Toy Story, uh, whose name rhymes with Shooty. And So just enjoy this. I'm going to run through a practice problem, help you guys, get through this tough time that we're going through right now of doing equilibrium calculations. And so hang in there and know that I'm with you. Okay, we're going to consider the following equilibrium system. This one is carbon monoxide, which is CO plus H2 yields CH3OH. That's also known as methanol, which is an alcohol that is not safe to drink. It's a different type of alcohol, usually called wood grain alcohol. So the carbon monoxides here, CO, hydrogen, and methanol. Okay, so we're going to consider that system going into this problem. Okay, so the question states 2 moles per liter CO, carbon monoxide, is placed into a flask with 1 molar H2 at a certain temperature. Okay. At equilibrium, we have 0.250 molar of the methanol in the container. And the question says, calculate the K. It asks you to calculate the K. So we're looking at the equilibrium constant calculation. So remember the first step, you want to get an ice table going first. Okay. And so when we look at the ice table, it can help us to organize our data. So you can see we have our 2 molar carbon monoxide, our 1 molar H2. We're starting off with 0 molar of the methanol, and it says at equilibrium, which is the E in the ice table. Remember, I is initial. We have 0.250 molar of it. Okay. So then that brings up the question, well, how do I get the other equilibrium concentrations? Because to calculate the K, we need the data for those, okay, the ones that are marked E on the ice table. So first thing we need to do is figure out the change for the one that we know. And since I know we started with 0 methanol and we ended up with that, the 0.25, the change is positive 0.25. Now, the next thing to think about is the rule. If the right side of the double arrow is positive, the changes for the left side need to be negative, okay? So we need to figure out how much the change is for carbon monoxide. Well, when I look at it, there's a 1 that's not written coefficient in front of CO, and we have 1 methanol, so that means their change is equal. That's what the balanced equation does for us. It gives away what the change should be. Now, if that's a 1 and that's a 2, then the change for hydrogen should be twice as much as the change for the carbon monoxide and also the change of the methanol. So the change for this one's going to be 0.5. Again, it's minus because it's on the other side of the double arrow. So the hydrogen's going to go down by twice as much as the carbon monoxide. The last thing to do with the ice table portion of the problem is to just do your math. So we have for the hydrogen it's 1 minus 0.5, which gives us 0.5. Real easy math. And the carbon monoxide, I had to use a calculator because I'm not real fast with the math. And I got 1.75. Now, those are the equilibrium concentrations, again, that we need to figure out the answer to this question. So we're really focusing on those guys when we're doing these types of problems. Okay. So the next thing is to take that and plug it in. So we plug in the values up at the top. We have our products on the top. Products always go on top, and it's divided by the reactants. And they're all gases, so they all go in here. So we have our value from the ice table for the methanol, for the H2 and the CO placed in there. We use our calculator, and we get 0.286. Now, K is less than 1, so the reactants are favored at equilibrium, but this is our calculation of the equilibrium constant for this problem.